Hi everyone. This week we'll be talking about measurable functions, which is also the title of this first video lecture. Measurable functions are at the core of probability theory and measure theory. So this first video lecture will introduce the abstract notion of measurable function. So we start with the definition, then discuss what happens when you compose measurable functions, the notions of pullback and push forward, and a criterion for a function to be measurable. Let us start with the definition. So when we have two measurable spaces and we define a function that goes from one measurable space to the other one, we say that this function is measurable, and if we want to be explicit about the fact that this definition depends on the choice of f1 and f2, we say f1, f2 measurable. If the preimage of any f2 measurable set, what is an f2 measurable set? Is just a set which is in this sigma algebra. So the preimage of any f2 measurable set must be f1 measurable. Yeah? So that's what is written in this equation. And the definition, of course, of preimage of a set is the set of all points that are mapped into that set. And we may omit this notation f1, f2 from the definition here if it's clear from the context which are these sigma algebras f1 and f2. Here is the second simplest example of a measurable function. The simplest example would be a function constant equal to 0, let's say. So we take a measurable space omega f, we fix some set A which is in f, so A is measurable, and we take a function that we denote by indicator of A. That's a function that maps every little omega in this set, capital omega, into a number 0, 1, and that number will be 1 if lowercase omega is in A, and will be 0 if little omega is not in A. So what does it mean to say this function is fp01 measurable? Well, this p01 is the sigma algebra of this very simple and elementary set 0, 1, and the sigma algebra is just the set of all subsets of 0, 1. And what does it mean to say that this function is measurable? It means if we take the inverse, the pre-image under this function, we get here empty, we get here omega, we get here A complement, and we get here A. This would be the pre-image of these sets by the function f minus 1, if we take f to be this indicator of A. And since these sets, each one of them by assumption is in f, this function is measurable. We now briefly mention that the composition of measurable functions is measurable in the right sense. And that means the following: if we have a function from one measurable space to another measurable space such that this function is measurable, and another function from the second measure space to a third measure space, which is also measurable, then their composition, which is a function that goes from the first space to the third space, will be a measurable function, of course with respect to this sigma algebra in the input and this sigma algebra in the output. The proof of this is very straightforward. So what do we have to prove? We have to prove that the pre-image of any set in F3 will be in F1. Okay, so let us denote age to be this composition. How does it go? We have to take first F and then G. Yes, so let's define age to be this composition. Oh, it is already here. So what we have to show is that age minus 1 of A is in F1. So of course the argument starts by stating let A be any set in F3, we want to show that the preimage of A is in F1. But as you can see already, there's not much left to prove. Why? Because H minus 1 of A equals F minus 1 of G minus 1 of A. By assumption, this is in F2 because G is measurable, and therefore this is in F1 because F is measurable, and that concludes the proof.